The next property of barycentric coordinates is very, very useful, but it's a bit harder to prove. Well, it is doable, but so let's do it. First of all, what are signed areas? Signed areas of triangles means areas of triangles taken with positive or negative sign depending on where the point P is. So if P is inside the triangle ABC, then all of them are positive. But if P is outside the triangle ABC, then some of them can be negative. It's just like this. So if this is, say, A, B, C, and P is here, right? Then in this case, the area of the triangle PCB is taken with a negative sign. But the areas of the area of the triangle areas of triangle APC and APB are still taken with the positive sign. Right, so the sign of the area is kind of changes when if you move the point P, and whenever it crosses the line BC, then the sign changes from plus to minus. So the sign of this triangle area of the triangle PBC changes from sign to minus. Okay? Now I'm going to do it only when in sort of in the simple case when P is inside the triangle ABC, but you can think about it and you will realize that the proof still holds if P is outside of the triangle only. Then you need to understand areas as signed areas. Okay, so let me erase everything and explain how to do this. Now, first of all, how can we do this? Now, barycentric coordinates, they do not depend on the choice of the origin, and here it is convenient to choose the origin at the point P itself, right? And if we choose the origin at the point P itself, then what we need to show is really just the following. So the area of the triangle PBC times the vector PA plus the area of the triangle PAC times the vector PB plus the area of the triangle PAB times the vector PC is 0. This is what we need to show. Okay, but then let's make a plot. So this is going to be my triangle. This is going to be my P. So let me denote this as A, this as B, and this as C. Okay, and let me choose angles. So the angle, the opposite internal angle from A is going to be alpha, the opposite from C is going to be gamma, and the opposite from B is going to be beta. So P is the point in the middle. I haven't labeled it. Okay, but then so if you think about it, so what are areas of triangles? So areas of triangles are going to be the product of the two sides. Like, I don't know, say if you look at alpha, so it's going to be the product of this side times this side times sine alpha, but then we multiply by PA2, so which means that we're going to multiply by this interval, right? So in all these three terms, we're going to multiply by the length of all the three segments from P to B, from P to A, and from P to C. So which means that we can just cancel them, right? So and this boils down, and 1/2 is going to be cancelled too. So this boils down to the following fact. So if we introduce unit vectors from P2 to alpha, if say this is the unit vector E1, from P to beta, this is going to be the unit vector E2, and from P2 to C, this is going to be the unit vector E3. Then what we need to prove really is that E1 times sine of alpha plus E2 times sine of beta plus E3 times sine of gamma is the zero vector. So how can we prove this? Now, there are different ways. I found a method based on the circumscribed circle online, but I think it's a bit hard to understand. If you don't remember the school geometry very well, it's a bit hard to understand. So I think it is easier to switch to complex numbers, right? So imagine that you place the origin. Okay, let me just make another plot. So if we introduce the complex plane, and if the vector E1 corresponds to number 1, E3 corresponds to, since this angle is alpha, then at E3 we have, stop, sorry. This is going to be E2, and this is going to be E3. Yeah, it is like this. Yeah, okay. So the angle from E1 to E2 is gamma. This is gamma. The angle opposite of E1 is alpha. I'm sorry. And the angle, yeah, opposite of E2 is beta. Right. So then what we need to show is that 1 times sine of alpha, sine of alpha plus, so E2, so which complex numbers sits at the end of E2? This is e to the power gamma I, right? Times sine beta plus e to the power, which complex number sits at the end of the vector E3? This is e to the power minus beta I times sine of gamma. And we need to show that this is 0. The complex is 0, so 0 plus 0i. But this is an easy exercise, and I encourage you to do it, to just write it down and verify that this is indeed true. And remember that the condition here is that alpha plus beta plus gamma is, by construction, is 2 pi. And if you compute it, you will see that this is indeed true. So it works. So barycentric coordinates of a point are proportional to the signed areas of the 3 triangles.